Okay, section 4.2 is really long, so be prepared. This is going to be 2 videos, but we're talking about related rates. So we just finished talking about implicit differentiation, where we treated y as a chain rule. When we do related rates, we're actually doing implicit differentiation again. So we're doing implicit differentiation, but we're doing it with respect to time. So what does that mean? Well, normally when we were doing differentiation with x and y, right, the notation we used was dy dx, okay? This means the derivative of y with respect to x. Okay, which is why we treated y as a chain rule. Y is in terms of x. And so whenever we were doing implicit differentiation before, we did it in terms of x, and that's why y was our chain rule. If we're doing things with respect to time, that means that our notation will look more like this. You'll have some dy over dt instead of dx. So if you have any variables in your equation that are not t, then all of them are treated as a chain rule, just like y was before. Okay, so let's practice this. The first one, we want to do implicit differentiation for the surface area of a sphere. So the first thing we do is, I'm going to write down the equation just so that, and I'm going to zoom in a little bit here. We have a equals 4 pi r squared. So the 2 variables we have in this equation are a and r. Neither one of them is t, so I have to treat them both as a chain rule. Okay, so think of the inside function is your t. Okay, even though we don't see t on the inside, we're going to treat this like it is an inside function. So I need to differentiate both sides of this equation. The derivative of a with respect to t, so the derivative of the outside is 1. Right? If a is some function of t, the derivative on the outside is 1, times the derivative of the inside, dA dt. That's just like what we were doing last time when we had the derivative of y was dy dt, dx. Now we just have t on the bottom. Now we're looking at the other side. So the derivative of 4 pi r squared. So that 4 pi is a coefficient in front of r squared. So when I do the derivative of r squared, I bring that 2 out front and I multiply it with what's already there. So now that becomes 8 pi r. That's the derivative if I was with respect to r. But since I'm with respect to t, now I also have to multiply it by dr dt. So rule of thumb when we're doing this implicit differentiation with related rates, if you have a variable that is not t, when you take the derivative, you multiply by the derivative of that, always. So dr dt for r, dA dt for a, dv dt if our variable was v, we would always multiply by that derivative. Okay? So this is just 1 times dA dt is dA dt, and then I have 8 pi r dr dt. Okay. So it asks us to do implicit differentiation, and then the next question it says, state what each rate in the differential equation represents. So we have 2 different rates here. We have dA dt and dr dt. So dA dt is the rate at which the surface area is changing. because in the original formula, A represented the surface area of the sphere. So it's the rate at which that number is changing. dr dt is the rate at which the radius is changing. Because in our original function, r represented the radius of that sphere. Okay. Let's do some more practice with this implicit differentiation. So on number 2, our formula, we have the volume of a sphere. So V equals 4/3 pi r cubed. That's the volume of a sphere. Differentiate both sides. So on the left we have just V. So the derivative is 1 times dv dt because there's no other number in there. There is no power. So it's just dv dt. Equals, that 4/3 pi is a coefficient for r squared, or r cubed, sorry. So when I use the power rule, I'm going to bring that 3 out front and multiply it by 4/3 pi, which leaves me with just 4 pi. And then the exponent goes down to a 2. But since I have a variable that is not t, I have to multiply by dr dt. Okay. So cleaning this up just a little bit, we have dv dt equals 4 pi r squared dr dt. Okay. So what do the two rates we have represent? Well, the two rates we have are dv dt, which is the rate at which the volume is changing, and we have dr dt again, which is the rate at which the radius is changing. Okay. The dt portion represents over time, so these rates are happening over time, the rate at which the surface area is changing over time. That's what that t on the bottom of this represents. Okay. Moving along, number 3, we have a equals the square root of c squared minus b squared, where c is a constant. So we have 3 variables in here, a, b, and c, but when I do the derivative, the only 2 that I need to multiply by their derivatives, dA dt and dB dt, are for a and b, because c is a constant. So the derivative of a constant is 0. So I don't have to put dc dt in here anywhere. Okay. I am going to rewrite this though because I do not like having radicals. I want to rewrite it as a power. Okay. So differentiate both sides. I should have rewritten it over here. So the derivative of a is just 1 times dA dt equals, now this is a chain rule, right? We have c squared minus b squared on the outside, and 1/2 is our power on the outside. So chain rule says derivative of the outside, so I bring that 1/2 out front, and then the middle stays the same. Subtract 1 from that power, times the derivative of the inside. So this is the part where we're going to use that dB dt, because the derivative of the inside, well, the derivative of c squared is 0 because they tell us c is a constant. The derivative of negative b squared is negative 2b dB dt. Okay. So now we can clean this up a little bit. We have dA dt is equal to that 1/2 and the -2 cancel each other out. So it's really just negative c squared minus b squared to the -1/2 times dB dt. Or you could also rewrite that dA dt equals, oh, I left off the b before. Sorry, that dB dt has a b in front of it. So if you rewrite that, clean it up even more, you could write that as negative b over the square root of c squared minus b squared dB dt. So the two rates that we have in this problem, we have dA dt and we have dB dt. And I'm not going to write this as two separate statements because they're not specific for anything. So dA dt and dB dt are the rates at which A and B are changing. Okay. Moving along, still we have now number 4, V equals pi r squared h, where r is a constant. This is the volume of a cylinder. So V equals pi r squared h. Take the derivative of both sides. The derivative of V is 1 times the dV dt. And now pi r squared is acting as a coefficient for h. So when I take the derivative of h, whatever was out front gets multiplied by the power. Well, the power is 1. So the derivative of pi r squared h is pi r squared. And then I multiply it, remember, by dh dt. So dV dt equals pi r squared dh dt. So the two rates, we have dV dt, which represents the rate at which V is changing, which V stands for volume. And then dH dt is the rate at which, wow, the height is changing. Okay. Number 5, we have cosine theta equals x over 15. I'm going to rewrite x over 15 as 1/15x. So then I have something to multiply with a coefficient and a power. So we have cosine theta equals 1/15x. Derive both sides. The derivative of cosine theta is negative sine theta, but theta is our variable. So I still need to multiply by the derivative of theta, which is d theta dt. Okay. And then the derivative of 1/15x is 1/15. And then multiply by the derivative of x, dx dt. And really that's it for that one. So the two rates we have d theta dt, which is the rate at which theta is changing. And you can see what theta represents in that picture. And then dx dt is the rate at which x is changing. Okay. Another way to think of this is really you're just taking the derivative as if the variable that's there is the variable we're in respect to, and then just always multiply by the derivative of that variable. So I took the derivative of cosine theta just as if theta was the variable that I was in respect to, just as if it were cosine of x, because the derivative of cosine x is negative sine x. The extra piece here is just multiplying by the derivative of theta. Okay. And finally, number 6, we have our volume of a cone, V equals 1/3 pi r squared h. So on this one, they do not tell us that r is a constant. There are no constant variables in this equation. They didn't tell us that there were any. So I'm going to have 3 different rates here, one for v, one for r, and one for h. Okay. So differentiate both sides. The derivative of v is 1 times v dv dt. And then when I get to the other side, this is actually a product rule. I have 1/3 pi r squared, and I have h. Those are 2 separate things that are being multiplied together. This is a product rule. So when I do the derivative, I need to use the product rule to take the derivative. So the derivative of the first piece, 1/3 pi r squared, the derivative of that is taking that 2 from the exponent and multiplying it out front to get 2/3 pi. And then r becomes r instead of r squared, times by dr dt, that's part of that derivative. So that's the derivative of the green piece, times the second, so the derivative of the first times the second, plus the derivative of the second, which is just 1 dh dt, times the first. Okay. So this is the derivative of the green piece. This is the derivative of the blue piece. Okay. So I'm going to clean it up just a little bit. We have dv dt equals 2/3 pi r, and I'm just going to pull that h out front of dr dt, plus 1/3 pi r squared dh dt. So the rates that I have in this problem, I have dv dt, which represents the rate at which the volume is changing. Dr dt, which is the rate at which the radius is changing. And then dh dt, which is the rate at which the height is changing. Okay. So that's a little bit more practice with this implicit differentiation in respect to t. So now instead of respect to x, with respect to t, we have to remember to multiply by that derivative of each and every variable that is not t. Okay. Let's do a problem together in this video, and then I might switch to the next video, just depending. I don't want to keep this too long. Okay. So we have air that is leaking out of an inflated balloon in the shape of a sphere at a rate of 230 pi cubic centimeters per minute. At the instant when the radius is 4 centimeters, what is the rate of change of the radius of the balloon? Okay, so I have this chart here to identify the steps for solving these kinds of related rates problems. So step 1, identify all of the variables that are involved in this problem. Well, because they give me the rate at which the air is leaking out of the balloon, that rate is in terms of volume, right? If the air is leaving the balloon, it's affecting the volume. So I know that we're talking about volume in this problem. And then also they say the radius as well. So volume and radius are my two variables that are identified in the problem so far. Okay. Number 2, identify which, if any, of the variables in the problem remain constant. Well, we know that the volume is not staying constant because they say that air is leaving. And we know that the radius is not staying constant because it's asking us to find how much it's changing by. So there are no constant variables. Okay. Number 3, identify the rates that are given and the rate that you wish to find. So they tell us that the air is leaking out at a rate, that's a key word there, of 230 pi cubic centimeters per minute. That is one of my rates. What rate is it? Well, that's the rate that my volume is changing. So this is dV dt. Okay. Centimeters cubed per minute. They don't give me any other rates as part of the information they gave me, but they did ask me to find, let's change color here, what is the rate of change of the radius? So we are trying to find dr dt. Okay. And I did not mean to put cubed there. The units on the radius is just centimeters per minute there. Okay. So number 4, it says write an equation, and most of the time it's a geometric formula or trig equation that relates all of your variables in the problem for which a rate is given or for which a rate is to be determined. So we want an equation that has V and R in it that relate these two things together. And V is volume. We're looking at the volume of a balloon, which we're going to just treat as a sphere. So the volume for this balloon is 4/3 pi r cubed. And this equation has V and R in it. So I will be able to use this one to find out what dr dt is. Okay. A trick here, substitute any value that represents a variable that is constant throughout the problem. We didn't have any constant variables, but at this point, this is where we would plug those in. Okay. Number 5, implicitly differentiate both sides of the equation with respect to time. So what we were doing on the last page. So our equation here, V equals 4/3 pi r cubed. The derivative of V is 1 dV dt. Remember that 4/3 pi acts as a coefficient to the variable r. So I take that 3 from the r, multiply it out front to get 4 pi, and then that r goes down to r squared times dr dt, because r is a different variable. So we have dV dt equals 4 pi r squared dr dt. Okay. Last step, substitute all of the rates that they gave us and the values for the variables that they gave us in the problem and solve for what's remaining. So in the problem, they tell me what dv dt is, they tell me what r is, and they want me to find dr dt. Okay, they said at the instant that r is 4, what is the rate at which it's changing. Okay, so they tell me what r is. The trick here is that our dv dt is actually a negative rate because the air is leaving the balloon. So the volume is getting smaller, it's going down, which means dv dt is negative. Just like if you were slowing down, that rate is negative because you're going slower. Okay, so for this one, instead of just writing 230 pi for dv dt, I'm going to write negative 230 pi equals 4 pi, and then instead of r squared, they want me to look at when r is 4, so 4 squared, and then I'm trying to figure out what dr dt is. So now I have negative 230 pi equals 16 times 4, which is 64 pi dr dt. I want dr dt by itself, so I'm going to divide everything by 64 pi. So I'm left with dr dt equals negative 230 pi over 64 pi. Those pi's cancel out. And I can plug this into my calculator and I get about negative 3.594 centimeters per minute. It makes sense that this is a negative rate because if air is leaving our balloon is getting smaller. So our radius should be going down, and that's why our rate here is negative. Okay. Let's do one more on this video and then I'll switch to a second video so you're not stuck watching this one forever. Okay. Our next problem, it says a stone is dropped into a calm body of water, causing ripples in the form of concentric circles. Okay. The radius of the outer ripple is increasing at a rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? Okay, variables that are involved in this problem. They did tell us that the radius is changing, so that is one of our variables. And something else that they're asking us to look at is the area. So radius and area are the variables here. Do any of them remain constant? No, because they tell us the rate of the radius is 1 foot per second. That's how fast that's changing. It's increasing. And then they ask us to find the rate the area is changing by. So there are no constant variables. What rates do they give us? They tell us dr dt. They tell us the rate at which the radius is increasing, and it's 1 foot per second. And then they're asking me to find dA dt. And the area is in feet squared per second. So now what equation can we use to relate radius and area? Well, it's area of a circle, right? These are concentric circles that we're talking about. So really, we're just going to use the formula for the area of a circle, which is pi r squared. So now we just have to take the derivative of both sides here. The derivative of a is 1 dA dt. I'm just going to write dA dt. The derivative of pi r squared, bring that 2 out front to get 2 pi r times dr dt. Substitute all the information we know. We're looking for dA dt. I do not have that. 2 pi, it talks about when the radius is 4 feet. So it says the instantaneous radius that we're looking at, so r in this problem is 4. And then the rate at which the radius is changing, it's increasing at a rate of 1. So dA dt would be all of that multiplied together, which is just 8 pi feet squared per second. Okay, I'm going to stop this video here, and the next video will just